Okay, after the code is coming to completion, at the end of scan of the temperature, it saves in the line 374 the record of all variables like magnetic field, the geomagnetic ratio, coupling, temperature in the fourth column, and the energy in the seventh column. Then this is accumulated in the variable scan, and then we finish the scan over the temperature. And just in case, if one wants to process the data by Excel or Origin, it is saved into file named scan. Now, at the next step, this line measures the size of the scan variable so that it will be universal independent of the parameters. And here, this line 388 and 389, I take the column number 4 into variable x, which will be temperature, and column number 7 into y. This will be this is average energy. So next interesting and important thing. So I redefine the no, wait. This is not needed. Okay. So in lines 409 to 412, one is making an average. So this line 411 is spline by hand. So the value of energy at step number I is added with energy at the next data point and previous data point, and then divided by number of points. And there is an average over several neighbors. So this procedure is needed in order to avoid fluctuations. And it is a standard way to process data with noisy data. Now, and once again, YY is energy. Is energy. So the next thing is the computation of specific heat as derivative of energy over temperature. So we save it into variable specific heat 1, and then in the line 425, we do the same trick as we did in the two labs ago. We need to fix the length of the array, since when we take differentiation, the array length is shrink, so we just add value 0. And now the if you plot temperature, which is in x-axis, and specific heat 2, it will be good. It will show what we need. So this data, this smooth data, are saved into the file smooth energy. And the last thing that one can use for visualization is to plot this data with along x. We use not absolute energy but relative thermal energy in respect to spin-spin interaction. Then in this unit's energy will be dimensionless and will be applicable not only to the system for ruthenium chloride but for any system with magnetic ordering. So this will be x-axis, and this will be specific heat which will be plotted by these symbols O minus, and then one can put labels. And after this, the code is stopping. So if you look into, yes, so if one practice this command, the line will look this way. And we do see the trend that heat capacity increases while number of accessed states becomes bigger with temperature, and then it drops. As a reference point, so this circles is data computed with this code, and this red line is a reference point computed in the same way as we did in the previous labs, based on non-interacting spins with hyperbolic tangent. So if you want, let me demonstrate it once again. So after code is ended, I type figure, and then I can type this plot stuff. From here, copy, paste, and here appears this figure. So this is the main result of this modeling, and we will run it with different parameters in order to analyze the mechanism behind it. So this should conclude this video, and I believe everyone in the class is ready to present. So I'll share this video as well, and to run it at a quicker time, I have modified the following parameter to make it quicker. So yes, so original version used the step 0.018, and I increased the step between different values of temperature 10 times bigger, and then it works for about 2 minutes on a specific laptop where I run. So I need to find the button to stop it and share the video with the class.